Think about this for a second. Every single material around us, yeah, the metal in your phone, the plastic bottle on your desk, even the concrete holding up a bridge, it has a secret rule book. It's this hidden set of instructions that dictates exactly how it will stretch, bend, compress, and, when it will eventually break. For centuries, figuring out those rules has been this slow, really painstaking process. Well, until now.
And that gets us to the absolute core challenge for pretty much every engineer and scientist out there. How can you possibly learn a material's secret rules without doing tons and tons of destructive tests? I mean, how do you predict when something's going to fail before it actually happens? This has been one of the biggest roadblocks in designing, well, everything. But a totally new approach is about to flip the script.
All right, first up, let's really dig into what this secret rulebook is and why it's been so incredibly hard for us to read.
So, the fancy scientific term for this rulebook is a constitutive model. But honestly, just think of it like a fundamental recipe. It's a set of mathematical equations that perfectly describes a material's unique personality, how it responds to any kind of push or pull you throw at it. If you get this recipe right, you can simulate its behavior with mind-blowing accuracy. But if you get it wrong, well, that's when things break when you really don't want them to.
And when you compare the old way to the new way, it's night and day. The old way of finding this recipe was, frankly, brutal. You'd have to physically pull, push, and twist little samples over and over and over again just to get a few data points. It was so slow, so expensive. The new way? You just let an AI watch a video of the material deforming, and it figures out the entire rulebook all by itself. We're talking about a massive shift from just a few data points to this rich visual information.
So how does this actually lead to a new way of thinking? Well, Section 2 gets right to the heart of the idea. We're talking about learning just by watching.
And here it is, the big, crazy idea. What if you didn't need to give an AI a bunch of specific force measurements? What if you could just show it a video? Show it the movement of every single point on an object's surface as it bends and twists, and the AI could reverse engineer the material's fundamental laws just from that.
Now, the research really hones in on this one super tricky property called elastoplasticity. And I know that sounds really complex, but trust me, you already know exactly what it is. Just grab a paperclip, bend it a little bit, and it springs right back, right? That's the elastic part. But then bend it too far and it stays bent for good, that's the plastic part. Modeling this two-stage behavior is notoriously difficult, which is what makes this breakthrough so darn significant.
And look, the researchers themselves just sum it up perfectly. This isn't just some tiny little improvement. They believe this new method could truly pave the way for a massive generation of material models. It's not an exaggeration to say this could completely change the game for how we design and understand the physical world around us.
Okay, so how on earth does this actually work? Section 3 pulls back the curtain on the clever mechanics behind it all, a really smart AI paired up with a very, very special teacher.
So the whole learning process works in this awesome loop. Imagine the AI is a chef, trying to bake the perfect cake, but with no recipe. Step 1, it guesses the ingredients. That's the neural network making its first guess at the material's rules. Step 2, it bakes the cake in a virtual oven to see what happens. That's a simulator predicting the deformation. Step 3, it compares its cake to the perfect one, which is our real-world video. And step 4, this is the magic part. The oven tells the chef exactly what was wrong with the recipe, so the next guess is way better. And this loop just keeps repeating, getting closer and closer to perfection every single time.
And the secret sauce to all of this is something called a differentiable simulator. This is our magic oven. See, a normal simulator can only go forward. You give it rules, it spits out an outcome. End of story. But a differentiable one, it can work backwards. It can look at the difference between the AI's prediction and reality and calculate the exact feedback the AI needs to fix its recipe. It doesn't just tell the chef, hey, your cake is wrong. It says you need a little less sugar, a bit more flour, and bake it for 2 minutes less. It is the perfect teacher.
Okay, so that's the theory, and it sounds amazing, right? But does it actually work? Section 4 is where we get the satisfying payoff. Let's see the results. So here's the setup. The researchers created this virtual experiment where they squeeze this notch block at a constant speed. This creates this really complex, non-uniform deformation pattern, which is actually perfect. It's rich visual data for the AI to learn from. This video becomes the ground truth that the AI has to try and replicate perfectly.
And the result is honestly stunning. On the right, that's the ground truth, what actually happened in the original simulation. And on the left, that's the AI's final prediction after it learned the rules. I mean, look at them. The patterns, the stress points, they are a near-perfect match. The AI actually did it. It learned the secret rulebook just by watching.
Now, this wasn't instantaneous, of course. The learning journey itself is fascinating. After just 10 tries, the AI's guess is pretty clumsy. You can see it only gets the basic idea. But by 100 repetitions, it's getting so much closer. And then, by the time it's gone through that learning loop 1,000 times, its internal recipe has evolved into an almost perfect copy of reality.
This is all incredibly cool from a technical perspective, but what does it mean for the real world? In our last section, let's just zoom out and talk about the massive implications of this kind of technology.
The applications here are just huge. We could design revolutionary new metamaterials with properties we've never even dreamed of. We could create movie special effects or video games with physics so real they're indistinguishable from life. We could speed up the design of safer cars and stronger buildings by understanding how materials fail with incredible accuracy. We could even build digital twins of real-world structures to predict wear and tear before it becomes a problem. This just fundamentally changes the speed, the cost, and the scope of material science.
And all of that leaves us with this one final, fascinating question to chew on. This method, learning by watching, combining a smart AI with these differentiable physics simulators, it's cracked the code for materials. So what's next? What other hidden physical laws, what other secret rules of our incredibly complex world are just sitting there, waiting for an AI to observe them and reveal their secrets to us?